Hello, I'm Sangal. Welcome to today's presentation on the fascinating topic of the lotus leaf effect. Have you ever wondered how a tiny leaf can ripple water so effectively? Well, today we will be exploring the science behind the incredible phenomena and its potential applications in various industries. Topics for discussions. We are gonna be discussing these topics in today's session. So what is lotus leaf effect? The lotus leaf effect, also known as lotus effect, refers to the ability of lotus leaves to repel water and self-clean through their unique surface structure. This effect has inspired the development of super hydrophobic and self-cleaning surfaces, which have wide range of applications in various industries. The lotus leaf surface has micro scale and nano scale structures that consist of numerous small bumps and wax coated hairs. This structure creates high contact angle between the water droplets and the surface, causing the droplets to roll off and carry away the dirt and debris. Mechanism behind the lotus leaf effect. The lotus leaf effect is a fascinating phenomena that has captured the attention of scientists and engineers. At its core, the effect is due to the unique surface structure of lotus leaf, which is covered in micro and nano structures that repel water. These structures create a rough surface that minimizes the contact area between the leaf and the water droplet, causing them to bead up and roll off. As you can see in the figure, these are the nanostructures what I was talking about. To understand this better, imagine a ball rolling down a hill. The steeper the hill, the faster the ball will roll down with it. Similarly, the micro and nanostructures of leaf create a steep slope for water droplets to roll down, allowing them to easily slide off the surface. This surface cleaning property is not only useful for the lotus plant but also many potential applications and in various industries. Super hydrophobic effect. The super hydrophobic effect refers to the ability of certain surfaces to repel water and resist wetting. Super hydrophobic surfaces are characterized by high contact angle between water droplets and the surface, typically over 150 degrees, and low contact angle hysteresis, meaning the droplet rolls off the surface with ease. The superhydrophobic effect is achieved through various techniques. These techniques create surface structure that traps air between the surface and the water droplets, reducing the contact area between them and making it more difficult for the droplets to wet the surface. Techniques used to prepare superhydrophobic surfaces. Chemical vapor deposition. CVD involves the deposition of thin films onto substrate through chemical reactions in the vapor phase. Sol-gel method. The sol-gel process involves the synthesis of inorganic materials from solution that undergoes chelation process to form a solid network. Electrochemical methods. Electrochemical techniques like anodization and electroplating can be employed to create superhydrophobic surfaces. Plasma treatment. This involves exposing the material surface to low pressure plasma, which can modify the surface chemistry and morphology. Nanostructuring techniques. Various fabrication methods can be used to create micro and nanostructures on surface, which contribute to the superhydrophobicity. Chemical modification. Surface functionalization with hydrophobic molecules such as alkylsilanes, example octadicyl trichlorosilane (OTS) can be employed to reduce the surface energy and create superhydrophobicity. Engineering applications of superhydrophobic surfaces. Electronics industry. Waterproofing the electronics. Superhydrophobic coatings can protect electronic components from water damage. Moisture resistance. Electronic devices exposed to humid environments or moisture-prone conditions can benefit from superhydrophobic coatings. Self-cleaning displays. Superhydrophobic coatings apply to the displays and touchscreen to repel water, oils, and fingerprints, making them easier to clean and maintain. Automobile industry. Anti-fogging windows and mirrors. Super hydrophobic coatings can be used on automobile windows and mirrors to prevent fogging and condensation formation. Self-cleaning surfaces. Applying super hydrophobic coatings to the exterior surfaces of the vehicle can facilitate self-cleaning by repelling water, dirt, and contaminants. Fuel efficiency. Super hydrophobic coatings can reduce drag of frictional resistance on vehicle surface, leading to improved aerodynamics and fuel efficiency. Aerospace industry. Anti-icing and de-icing. Super hydrophobic coatings applied to aircraft surfaces can prevent ice formation or facilitate ice removal. Drag reduction. Super hydrophobic coatings on aircraft surfaces can minimize frictional drag during flight, leading to improved fuel efficiency and reduced emissions. The water repellent property helps maintain a smooth airflow over surface, optimizing aerodynamic performance. Corrosion resistance. Super hydrophobic coatings can protect aerospace components from cor- corrosion caused by exposure to moisture, rain, and harsh environments. Self-cleaning surfaces. Self-cleaning surfaces are the surfaces that are able to clean themselves without the need of manual cleaning. These surfaces are typically super hydrophobic and have high contact angle with water, which causes water droplets to bead up and roll off the surface, carrying away dirt and debris. The principle of self-cleaning surfaces is based on two main mechanisms: the reduction of surface energy and modification of surface texture. These mechanisms work together to minimize the adhesion of dirt, water, and other contaminants, enabling the self-cleaning effect. The principle of self-cleaning surface. Low surface energy. Self-cleaning surfaces often have low surface energy, which means they have reduced affinity for liquid and solid particles. Materials with low surface energy repel water, oils, and other substances, preventing them from adhering to the surface. Lotus effect. This is a phenomenon observed in nature on the leaves of lotus plants. This is a classic example of self-cleaning surfaces. Micro surface, okay. Microstructured surfaces. Microscopic or nanoscopic surfaces can be engineered or naturally occurring on a surface to create a roughness that limits the contact between the surface and contaminants. External factors. While surface properties contribute to self-cleaning, external factors like water, wind, or light often play a role in activating this self-cleaning process. Applications of self-cleaning surfaces and coatings. Architecture and building materials, solar panels, automotive industry, electronics, textiles, medical equipment, kitchen and bathroom surfaces, air conditioning and ventilation systems, food and beverage industry. The lotus leaf effect has immense potential in the field of bio-inspired materials and mechanisms. By understanding and replicating the micro and nanostructures on the surface of lotus leaf, we can create super hydrophobic and self-cleaning surfaces, water repellent fabrics, and anti-fogging coatings that have numerous applications in various industries. The lotus effect is not only fascinating from scientific standpoint but also has practical implications. As we continue to research and develop this technology, we can expect to see even more advancement and applications in the future. It is exciting to think about the possibilities of using nature as inspiration for solving real world problems. Thank you for listening to my presentation on lotus leaf effect. I hope you found it informative and engaging. Now I would like to open the floor for question and answers. Please don't hesitate to ask any questions or share your thoughts on this fascinating topic.